right. Moving on, we're moving on to chapter 15. Chapter 15 is called sampling distributions. Now, we have looked at a couple of distributions already. Can you name them? What are the distributions we've looked at? Normal distributions. Yep, the normal distributions, that's the bell shape. And the standard normal distribution is that table that we use, right? That I told you to keep close by for the rest of the course because we will be using it. And there's also, what other distributions did we look at? The box plots, yeah, those are distributions, but I'm thinking of like a parametric distribution where we tried to get the areas under the curve. There's one more. Yes. Uniform. Yeah, the rectangle, right? The uniform where every probability between A and B is equally likely, right? So we looked at those. This here is called the sampling distributions. So if I take, remember how we talked about taking a random sample from the population? Let's say I take a random sample from the class, let's say 15 of you. I can maybe take the 15 and go, okay, here's a random sample that can estimate what the full class average is for the midterm. So I could just mark 15 and get an idea from that sample. And that sample actually has a distribution. It's called the sample distribution or the sampling distribution. And we'll see what we can do with that. So we look at parameters and statistics, and we look at statistical estimation and the law of large numbers, sampling distributions in general. What can we do with these? The sampling distribution of X bar, that's the mean, if you remember way back from chapter 2, and the central limit theorem, and the sampling distributions and statistical significance. So moving on to here. Now, remember how we could do this in chapter 12. We could go, here's the women's heights, and they follow a normal distribution. We have a mean and a standard deviation, and let X be the height of the woman. And we can figure out if we were to randomly select a woman from the population, we could figure out what's the probability of her being taller or shorter than 172 centimeters. And we know how to do this. This is the process right here. We find the Z-score and we use the table, and we have our area under the curve, which is equal to the probability. But what if 4 women were randomly selected instead of 1? What if 4 were selected and we wanted to know the probability of the 4 women's heights average? Their average height was shorter than 172. And so this chapter will help us with that, solve that question. It gives us the tools we need to solve questions like this, okay? So just not selecting just one person from the population, but a group, a sample, right? And seeing if the average of the sample is greater than or shorter than 172. So we're going to come back to this question once we figure out how to use it, okay? So some terminology, a parameter, and a statistic. So what we're going to do is we take a sample from the population to draw conclusions about the population. And a parameter describes the population. And we've seen some parameters. We've seen mu and we've seen sigma. Those are parameters, and they represent the full population. So that would be the population mean mu and the population standard deviation. Versus a parameter. We're going to see right here. So the parameters describe the population, and the statistic describes the sample. The measure of center. So we have the measure of center, mean mu, is for the population, and the statistic would be the sample, X bar and S. So the parameters starts with the word P, and so does population. Statistic starts with S, and so does sample. And that's how you can keep them straight. So this is starting with an S. Well, first of all, these start with P, right? Parameter and population, and then a statistic starts with S. So we use the sample mean and the sample standard deviation to estimate the population mean mu and population standard deviation sigma. Right? We take a sample, and so these are estimates. These estimate an unknown parameter. So parameters come from populations and statistics come from samples. So X bar estimates mu and S estimates S. That's how we do it. We can have X bar estimates mu and sorry, that should be S estimates sigma. S doesn't estimate itself, it estimates sigma. These are the parameters, these are the statistics. Yes. Mean and mu. Depends on what we're talking about. If we're talking about the sampling distribution, the sample mean is, we say it's equal to the population mean. But if it's to answer a question like the previous slide, where X is 172, then it's X bar is 172, then it's not the same as mean. So it depends on the question. Just, we want to keep these straight, that X bar and S are estimates, samples, right, from the samples, and mu and sigma are parameters from the population. And so you might hear me say the true mean. When I say the true mean, I'm meaning the population, because that's the true. The sample is just an estimate, so I can't say it's true. I can say it's close, though. Based on the sampling distribution, I can say it's close. You'll see why here. So the process of inference, that's where we're estimating, and that's what we're doing here. We're setting the stage so that we can use these tools to estimate, and that process is called statistical inference. Right? It leads us to confidence intervals and hypothesis tests and all those good things. Right? So we need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. So we can think of the statistic as a random variable because it takes on numerical values. So the process is we take a sample from the population. Remember, the sample is a subset of the population. That would be like equivalent to me taking 15 of you and just marking those midterms and using, like, just randomly choosing 15, let's say, and using those to estimate the whole class, or taking maybe a bit more to get a better estimate. Maybe I take 30 students, 10, 24 students, and get an average. And then I get a representative sample, and then I can say, well, this is what the average is probably close to being. It's going to be. Right? So you can think of it that way. If I took the first 2 rows here and calculate your midterms and take the average of the first 2 rows, do you think I could use that average and go, well, this is probably close to the whole class? Might be. Right? And we'll see how this process works and whether we can trust it or not. We'll see. So we start with the law of large numbers. X bar is rarely exactly right. So if I did take the first 2 rows and calculated the average midterm grade and then said this is close. It's not going to be exact, but it might be good enough, right? It varies though from sample to sample. And why is it nonetheless a reasonable estimate? And here's one answer. If we were to keep on taking larger samples, let's say instead of taking the first 2 rows, I take the first 3 rows, the first 4 rows, and I keep increasing my sample, then I'm going to get closer and closer to the true mean mu, right? So X bar is the average that I would get from the sample. And as I increase the sample size n, I'm going to get actually more accurate as I go. Does that make sense? Just in your mind, you can go, yeah, more. If I add more students to the pool, I'm going to probably get closer to the true average grade, right? Make sense? If I took just 3 of you, it's probably going to be, it's just going to be so random. But if I took 4 grades and 5 grades and 6 grades and 7 and 8 and 9 and 10 and keep on going and get close to 30, then I'm going to get more accurate. And that is the law of large numbers. So you draw observations at random from a population and with a mean mu. And as the number of observations drawn increases, so as n increases, the mean X bar of the observed values tends to get closer and closer to the mean mu population. It's called the law of large numbers. And intuitively, it makes sense. More data, you're going to have a better estimate. So the sampling distributions, if the law of large numbers assures us that if we measure enough subjects, the statistic X bar will eventually get very close to the unknown parameter. Remember, I don't know the true value of the mean mu, but I'm trying to estimate it with the sample, right? If you took every one of the possible samples of a certain size, they're all the same size, calculate the sample mean for each sample and graphed all of those, ta-da, we have the sampling distribution. So if I take all of your names in a hat and I pull out 5 and I calculate the average midterm grade, then put them back and then take out another 5 randomly and calculate the average midterm grade and keep doing this over and over and over, I'm going to have a whole collection of averages, and that collection of averages is the sampling distribution for grades. And you end up with the average of the average. Then you have a list of all these averages, and then you can get the average of the averages. And it will be very close to the true population mean mu. And we use software to imitate chance behavior to carry out these tasks. So we have the sampling distribution. So here's the population, let's say, right? Population is here. And I take a sample and I get an X bar. Then I take out another sample and I get X bar 2. And then I get another sample and I get X bar 3. And I just keep going till I have X bar, I don't know, let's say 10,000. Can do this over and over. I can go to 1,000,000. On the simulation, you'll see in a moment, I go to 1,000,000. And if I take I can't take all possible samples because that's infinite, right? I can't get infinite on the computer, right? But we can imagine if we took a lot, 10,000, 100,000, 1,000,000, all these are going to be a collection together as the sampling distribution, and we call it formally the sampling distribution of the sample mean, because that's what this is. This is the sample mean. We have a whole bunch of sample means. And you might be going, well, what are we going to do with this? We're going to use this sampling distribution to answer questions like we saw on the first slide with the heights. So the population distribution, that's what we're used to seeing. That's just going to be of a single variable, just 1x. But the sampling distribution is going to be the distribution of values taken by the statistic of all possible samples. In this case, it's all individuals. Here, it's all samples. And you can do it not just for the mean. You can get the sampling distribution for the median. You can get the sampling distribution for the standard deviation. You can, so long as you're taking all possible samples and you're calculating, but the mean is what everybody wants to know. Nobody has ever come up to me and said, what is the median grade? What is the standard deviation? Nobody cares. They want to know what is the average. So that's why, and that is such a natural thing to analyze. We want to know what the average outcome is. What's the average height? What's the average age? What's the average score? And so on. So this is why we focus in this course on the sampling distribution of the sample mean. So it says here, be careful. The population distribution describes the individuals that make up the population, and a sampling distribution describes how a statistic varies in many samples from the population. So there is that distinction. And here we are. The population is going to be the flatter curve. The flat one is the population. And if I take all possible samples of the same size, like all those X bars, and we do like 1 million of them, all possible, then I'm going to end up with a very narrow curve. And the reason for that is because the standard deviation is much smaller for the sampling distribution than it is for the population distribution. It's just, that's how it mathematically works out. So taking the standard deviation of averages is much smaller than individuals, because individuals will have more variability than averages. Remember that thing we did in chapter 5, ecological correlation. Averages had a much stronger correlation and smaller standard deviation than individuals. So this is why the population will always be has more variability than the sampling distribution. In repeated samples, that's how we build it. So when we're choosing these samples, we're using an SRS from the population of interest, and it's the simple random sample, right? That means every subject has an equal chance of being selected. And once we do that, we just build them as SRS of size n, drawn from a large population with mean mu and standard deviation sigma. And the mean will be the same. The mean X bar will have a distribution with mean mu and standard deviation sigma, not just sigma, but sigma divided by square root n. And that is mathematically why the standard deviation is more narrow. So the standard deviation is not just sigma for the sampling distribution, it's sigma divided by square root n. And n is the number of samples, the sample size that you take, the sample size. So all possible samples of, say, size 30, right? And because the mean of the statistic X bar is always equal to the mean mu of the population, it's always centered at mu. We say the statistic, we just say that it's unbiased. There's more to that in a much more advanced proof, if you will, like a mathematical proof, but just take my word when I say it is an unbiased estimator. It's an unbiased estimator because it equals. And because it equals and we have the proofs in the theory, then we can trust it. It works. You can trust the result. So on any particular sample, when you take just one sample, we're not going to take all possible samples in real life. We just take one sample, but we use the theory to answer the questions. So we take one sample, it may fall above or below the true mean, but remember, we never know what the true mean is. We never know. We can estimate it with X bar, right? And there they are there. Let me just see. Yeah, so I think we'll take a break, and when we come back, I'll show you the simulation using grades, and I'll show you how we can build one of the central limit theorem, which is a theorem in the book here in this chapter. It's one of the most remarkable theorems in science, not just statistics. So we'll do that when we come back. So we'll take 10 minutes.